Okay. Thanks for introduction. My name is Barak Nehoran, and this work is about a new construction of public key quantum money in a black box model known as generic group actions. As you might have noticed, I am not the author, but since Mark could not be here today, he has asked me to present it on his behalf. You can feel free to ask me clarification questions, but for deeper discussion, feel free to reach out to Mark by email. So quantum money is called money because that's the most stereotypical use case. But really, the word money is a stand in for any verifiable object that you would like to prevent from being copied. And it solves the double spend problem, which is where an adversary has a single copy of an item, say a banknote, and wants to give it to both Alice and Bob. And wants to convince them that both of them that they have the unique original item. This can encompass anything from original art to deeds for property to event tickets, but we call all of these things money. And classically, there are two solutions to this. The first is using a physical object like cash, coins, gold, or a printed ticket. And to transfer this money, you need to hand over the object itself. But there's no provable security. And that is to say that with enough resources, you can make a convincing copy. And the second option, the second solution classically, is called digital currency. And these are things like credit cards, like bank wire transfers, or cryptocurrencies like Bitcoin. And all these things can be sent easily over the internet. So that's great. But the thing is that all these transactions require a trusted third party. For credit cards and wire transfers, this third party is the bank. For cryptocurrencies like Bitcoin, this is a shared public ledger, which is maintained by the community as a whole. But in any case, this third party ensures that the money that you're spending is yours to spend. Which means that there's this disadvantage that you cannot perform the transactions directly between users. So if I meet someone on the street, I can't directly give them the transaction. We have to involve someone else to verify the transaction. So can we get the best of both worlds? And this is where quantum comes in. The important feature of quantum mechanics that we'll need here is called the no-cloning theorem. And this states that given an unknown quantum state, it is in general impossible to produce two copies of the same quantum state. And no cloning is crucial for quantum money. In fact, quantum money was the first quantum cryptographic protocol. You might have already seen it mentioned in Anne's tutorial yesterday. So I won't go into too much detail, but I urge you to see her tutorial if you want more details. But just to recap, it was invented by Stephen Wiesner in the 1960s and 1970s. And the banknotes are quantum states that are unknown to the public. And the no cloning here implies that it's impossible to counterfeit. The problem is that only the creator, which we call the mint, knows the state, which means that only they can verify. So for example, if Alice wants to send her banknote to Bob, Bob has to send it to the mint so that the mint can verify it for Bob. Which means that we still need a third party to interact with us for each transaction. So this is why in 2009, Scott Aaronson proposed the idea of public key quantum money. And here, there's a public verification procedure that's known to everyone, which means that anyone can verify. The mint only creates the state, but is not involved in verifying it. So this behaves much like physical currency in the sense that the transactions are verified locally and instantly, but it also has the advantages of digital currency in the sense that it can be transmitted over the internet. Now, the thing is that because the verification procedure is public, it's information theoretically broken, which means that, in other words, you can brute force it, which means that we need to use cryptography and computational assumptions in order to achieve this. So let's talk about some of the existing schemes for public key quantum money. And so most the existing scheme, public key quantum money schemes kind of fall short of having a convincing justification for security. And they fall into these three categories that I put into columns here. The first is conjectured security schemes. And these are ones for which intuition exists on why cloning should be difficult, but they lack the rigorous justification. Unfortunately, they kind of have a poor track record. And as you can see, most of the schemes in this category have been eventually broken. These are the red X's. And this emphasizes the need for rigorous security justifications under widely believed assumptions. The second category is the black box model. And here, the adversary is constrained to operate in a prescribed manner by interacting with this black box. And it offers unconditional results without relying on any assumptions. But here, the interpretation of the proof varies, and it's not always clear how useful they are for ensuring security of actual real-world schemes. And in fact, many schemes that are based on them are in the left category here and are ultimately broken, indicating that the model might be a bit too restrictive. And then there's the third category, which is proofs under widely studied assumptions. This is considered the gold standard. And the thing is that even here, the strength of the result depends on the meaningfulness of the underlying assumption. So for instance, the only positive example here in this last column is this proposal, this construction of quantum money from indistinguishability obfuscation by Mark Zandri. And this is a setting where the Aronson-Christiana scheme is actually provably secure under an appropriate computational assumption, this assumption of indistinguishability obfuscation. And this is indistinguishability obfuscation is widely studied in cryptography, but unfortunately, the post-quantum security of indistinguishability obfuscation is not well understood. And there are other the other prior work. One that'll specifically mention here is this one called walkable invariance, and it encompasses various schemes, including knot-based schemes and new elliptic curve instantiations. It offers computational assumptions for proving security within the framework, but it's unclear if existing schemes meet the necessary conditions for this framework security. And unfortunately, also this current work contains some evidence suggesting that the assumptions here might be false, although this aspect won't be covered in this talk due to time constraints. So this work introduces a new construction of quantum money from the framework of Abelian group actions. So let's start by talking about what Abelian group actions are. So Abelian group actions consist of an Abelian group G and a set X. And we say that the group acts on the set X through an operation star, which we call the group action. And each group element acts on a set element by mapping it to another set element. So you take an element from the group, an element from the set, and it outputs a different element from that same set. And we require that it is compatible with the group operation, that this star operation is compatible with the group operation. And what this means is that the composition, if we have the composition of the actions of two group elements G and H, then this is the same as the action of G plus H, where plus here is the group operation. And we make the following assumptions. The first is that the mapping between G and G star X is a bijection. That is, for any two set elements, there is a unique element G mapping between them. The second is that the set X is sparse and recognizable. And recognizable means that you can officially check the membership in the set. And the third is that there's an explicit starting element that's known to everyone, this element X. And we finally want it to be computationally difficult to find this group element that maps between two set elements. So we said above here that there should exist such a group element. We want that it is computationally difficult to find it. And this is a task which is usually called the discrete logarithm problem. So now let's get into the construction. First, I'll describe how we mint. So we prepare a uniform superposition over the group and use it to act on the starting element X. And note that the uniform superposition up here can be prepared by doing a quantum Fourier transform on the identity element. We then do a quantum Fourier transform on the first register, and then we measure it. The classical outcome becomes a serial number H, and the rest becomes the quantum money state. Note that another way to look at this quantum money state is as a uniform superposition over the set elements. So each of the elements of this superposition is G acting on this initial element X, and this runs over different set elements. So it's a superposition over set elements, where the phase here depends on the discrete log G of each of these elements and the serial number H. So now how do we verify? First thing we need to do is we need to check that the banknote is only supported on the set X, which we can do efficiently by the assumption that we made earlier. Next, what we do is we once again prepare uniform superposition over the group elements U, and then use it to act on the banknote. So now let's take a closer look at what we have at this point down here. Let's first move it up there. We have the composition of two group elements, U and G, up here. And so we can rewrite this composition as the group operation plus by the compatibility property that we mentioned earlier. And then we can re-index the sum over G as the sum over G prime, where G prime is U plus G. Now, observe that in the register on the right here, what we have is just the original banknote. And in the left register, we're magically left with the Fourier transform of the serial number H here. So this allows us to measure the serial number of any purported banknote. Now let's talk about the security of the scheme. Can an adversary produce two banknotes with the same serial number? Well, let me convince you that for security, discrete logs have to be hard. And that's because suppose that they were easy, then we could do the following. So first we prepare a uniform superposition of the group elements. And then we act on the starting set element, X. Then we add a phase that depends on the group element and the serial number. And finally, we perform a discrete log in order to uncompute the first register. And notice that this gives us a new banknote for the serial number H, which means that we've broken the quantum money scheme. So this shows that we need discrete log to be hard. And of course, this uncomputing step at the end is what fails if the discrete log is hard. So now that we have this intuition, we can state the form. We can more formally state the main theorem of the paper. which is that the following assumption, which we call assumption 1, implies that the black box security of the protocol. And the assumption states that if we're given an element x and u acting on x, then it's computationally hard to distinguish the action of twice u from the action of a random v, from a random group element v. A technical note is that here we allow the adversary to make a quantum query to either the action of 2u or to a random v. And also note that this is very similar to a Diffie-Hellman, a decisional Diffie-Hellman-like assumption, where you have g to the we have g to the a, and g to the 2a, or you have g to the a, or a random element. If you don't know what that is, don't worry about that. An important remark here is that by a result of Edinger and Hoyer, the query complexity of discrete log is polynomial, which means that you can't have a conditional black box lower bound in the generic group action model. And for many, this meant that this generic group action model was not useful for proving security in the quantum setting. But this work challenges that understanding. For context, security proofs in crypto typically fall into one of two categories. We have the standard model, in which you reduce the security to a computational assumption. And we have the black box model, where you use query complexity techniques to prove the security directly and unconditionally. Now, because of the Edinger-Hoyer result, we see that any quantum proof in the generic group action model must use both. And remarkably, this is the first post-quantum security proof that makes use of black box group action. So the proof of the reduction is really neat, but I don't know that we have enough time for it, so I'll skip it for now. But if you're interested, feel free to come talk to me afterwards, or take a look at the paper. I urge you to look at it. It's a very neat proof. Let's skip through this. Okay. So to recap, this work introduces a new construction of public key quantum money from the framework of Abelian group actions. And crucially, the security of this scheme comes from a plausible Diffie-Hellman-like assumption on group actions. The paper also does a few other things, which are mentioned here. It also shows how to instantiate this construction with an extension to isogenies over elliptic curves through the framework of what's called restricted effective group actions. And it also compares various idealized models for group actions in the quantum setting. And it does a cryptanalysis of a knowledge assumption that's similar to that used by Liu, Montgomery, and Zandri that I mentioned earlier. So I urge you to check out the paper for more details. Thank you.
The audience could come to the standing microphones.
Hello. Hi, thanks for the talk. I wanted to ask, you presented it from this like perspective of abelian groups, but can you just like use a specific one? Like you talked about discrete log, so is it good enough to just pick like arithmetic modulo some like prime and like you can get this construction to work with that as well? Or like are the specific constructions are like more complicated than that?
So you need something that's quantum secure, right? And as far as I know, the the only ones that fit the bill right now are these isogenies of elliptic curves. They're one of the leading candidates for post quantum security. But I'm not sure if there are any other possibilities of instantiating this group action.
Okay, so I see. I was confused by like the fact that discrete logs like hard for classical computers, but like for quantum money to work, it needs to work against like quantum adversaries, and so that's why you need like post quantum stuff like this one. I see. Okay, thank you so much.
Yeah, thanks for the great talk. Do you mind just like repeating the last thing about the distinction between proofs by security reduction and proofs by like black box like query complexity lower bounds? Like I didn't quite grasp what the differences between these two things.
Should I go back here?
Yeah, this is it. Yeah.
Yeah. So this is actually like a subtle point here that so we have in classical, sorry, not in classical, but in like the standard cryptography, we have two types of proofs. We have the standard model proofs where you reduce it to an assumption, computational assumption, and then we have the black box model proofs where you prove something unconditionally in a black box setting. And the thing is that here, because of the subtlety, where discrete log is actually easy in terms of query complexity. The query complexity of discrete log of group actions is actually polynomial, which means that if you wanted to have a lower bound in the black box setting, you wouldn't be able to do that because your query complexity would be polynomial. But that doesn't necessarily mean that the actual complexity is polynomial, because you have to do something super polynomial in between, like the computations in this Edinger-Hoyer result. The computations in between are very inefficient. It's only the query complexity that's polynomial.
Okay.
Which means that you can make if you add the assumption of the discrete log being hard, which is a computational assumption, then you get this proof using both of these things. And it's kind of because of this Edinger-Hoyer result, it's kind of required that you have to use both. Does that make sense?
Yeah, thanks. That really helps. Yeah, thank you.
Hi, thank you for the talk. It was very interesting. I have a possibly very naive question. Could you go back to the intuition you gave for why discrete log needs to be hard?
Yes.
I didn't get a super good look on this slide, but it
Sure.
seems like you can compute, you can map a superposition over G, map a superposition over G to a superposition over G comma G star X without any leftover junk or states. So then, like, can we not generically also decompute the input? As in, I would expect there to be more in that first step. As in, we map G to G comma G star X.
Yeah.
And this is some unitary operation. So can we not then also decompute the input, since the G to G star X is a bijective operation?
Yeah, so
map.
Because it's bijective, yeah, it's a good question. So the question is, because it's bijective, why can't you uncompute G?
Yeah.
Yeah. So because it's bijective, there is an information theoretic way to uncompute G, but because discrete log is hard, there is no way to do that, because essentially that is it's the task of solving the discrete log. You go from G star X to finding what G is.
Sure, but this mapping is a unitary mapping, right? There's no leftover junk. Usually when we have these, at least in my experience, when we have these hard to invert operations, there's some leftover junk that means the operation is not just unitary. So
Yeah,
maybe
so
I'll take
it is unitary. It's just it's just a complicated unitary. It's a unitary that will
maybe I'm
be
missing
inefficient.
something. I'll ask.
Does that make sense? Like, it is a unitary. It's just an inefficient one.
Oh, okay. And so the first step as well?
No, this first step is efficient, because you can do the group action efficiently. You just can't do the discrete log efficiently.
Okay, I'll just ask the specific.
Maybe we can talk offline about it.
All right, that's all we have time for questions. Thank you, Barak.